那个访谈是最好的，这个真的是没有。但其实我觉得核心就是它那个方块放大的时候，我们是8×8嘛，8×8，跟8×8没有，这个其实没多少倍，没多少倍，我们看的就大概的预算。对。如果没事做的话，可以去你们家附近有家，你们家是200、900、700、800，
So I like Starman. So she was like, oh, he's right. This is super easy. Just to like implement this algorithm. So I was caught up with her so I took the second one last night. It's like and I'm just like, oh, this is like a little. I just somewhere in there, I just like get something so good because it's like almost right. It's wrong in the exact same way that they're just completely wrong the first time. Instead of indexing your rate by the high, I'm indexing it by 1. So you would say the same thing. So like cool, I've had it fun. Come back, and it's like not small.
It's not a smaller.
Well, it is. Just like I've known this, but it's just people register. It was like I never thought, well, okay, not something that's a freshman forever. Because like the algorithm iterates.
Tuesdays?
Yes.
Yes, I do.
So,
I like the small amount.
but
I can't send an email, the files are too big and the server rejects it. So you have to come up with some kind of drive, something. This needs to fit in the Dropbox.
So that was like, I finally realized that it was like some of them like a few hours.
Unless you have room in yours.
It's like,
yeah.
So I can use my email and you can.
It's you directly compare the loads.
Thank you.
yeah, so, well, okay, so I think I heard about like, you know how like loads are
Yes.
so you can't directly compare loads because like it might be different. So this one was off by,
Thank you.
I thought,
We should be. Caleb needs 1 more minute.
Just let me know when you're.
Yeah, it's actually recording right now. So
It's recording too.
yeah.
I've done it before. So for instance, like, go to parentheses 1 minus 1. It's about
Yeah,
or sorry, 1.0.
it's about 3 days.
That makes a difference.
Well, you can't draw. You might be able to find one of those.
But just doing it, you're just
Very.
Yeah, you can just subtract one.
Both hands?
Are there fairies?
Oh, yeah.
They're like
Oh,
cards.
okay, then that's fine. I always do.
I think that's very across the Great Lakes.
Or there are fairies that go across the Bering Strait.
Oh, across the Bering Strait now.
Yeah.
Yeah. Yeah. So the tension between Russia and the United States is still high enough over the Bering Strait.
That's great.
It's too cold to care in the Bering Strait.
You would think.
All right. So let's start. Approximations. We're continuing them, and today we'll start with another problem. The traveling salesperson problem, and there's actually a movie out based on this. I have no idea how good it is, but people like to get very excited when they make movies about stuff like this. So there is a movie out, and I'm sure it's very good, and you all will see it. Excellent. It involves the NSA, someone who, this is basically, you have to understand, this is a computer scientist sort of dream scenario. Someone figures out a solution to the traveling salesperson problem, and now the NSA is pursuing them, sort of because this will unlock some secrets of the universe or something like that. So this is what I dream about at night. So, but let me tell you what the problem is with things. Right? It's a very simple problem. I have some region, and I have locations. Different locations. This is a roof of a house, in case you're wondering. And you have to go and deliver things to them. You have to deliver things to all of them. In this particular version of the problem, you're trying to sell something. Of course, no one ever goes through selling anymore. But back in the day, when dinosaurs roamed the earth, people would go around selling things door by door. And so then, what you need to do is figure out a way to visit all the houses in some order, that minimize your time. Of course, you don't want to go back and forth, that waste gas. So maybe you go, I don't know, let's see, maybe you start here, you go here, like this, maybe like that, and then like that. That could be one possible way of doing things. Or maybe your dream vacation is to visit baseball stadiums in every single one of the 50 states. I know someone whose sabbatical is basically that. And so you want to find an efficient way to get from one baseball stadium to the next. And then you can imagine the map of the US. So the goal here is to visit all the locations and minimize the amount of distance you travel in doing so. So in general, you have some kind of metric space. And a metric space means there's some way of defining distance. So there's some distance function, which given 2 points, x and y, will tell you how far apart they are. And because this is a metric space, we have what is it? First of all, it's symmetric. The distance from you to yourself is 0. Distance from you to there is distance from there to you. But also you satisfy this thing called triangle inequality, which means that if I look at the distance from x to y, and the distance from y to z, that distance, the sum of those two things is always worse than just going straight across to z. So shortcuts are good. Okay. So in such a space with a distance that satisfies this property, like your distance or Manhattan distance or block distance or whatever you want, as long as there are no one-way streets, you have this property. So it's not a very taxing property. And then the goal is to find, so you're given the sites which are x, and a distance function that's defined on x, find a tour, which is basically a sequence of x1 up to xn, such that the sum of the distances from xi to xi plus 1, and then cycle back. Being lazy, not write them once, but you get the idea. Is okay? So it's a well-defined problem, or hopefully it's a well-defined problem. Any questions about this problem? No? Makes sense? Okay. And needless to say, this problem is NP hard. We don't know how to get an exact algorithm for this problem, and we also believe that if we did, we'd solve everything else. That's NP hard. So the question then becomes, can you approximate this? Can you get an answer that's close to the optimal solution, if not exactly? And I should say that if you're in the plane, what we now know is that you can actually do this extremely well. You can get one of those 1 plus epsilon approximations that I mentioned. You can arbitrarily close to the right answer. So if your map was in fact a set of US states and you wanted to visit baseball stadiums in every state, you could do this as precisely as you wanted. But in general, for a metric space, which may not be a nice flat Euclidean space, could be something more complicated, that may not necessarily be true. But we'd like to get something in. So as always with approximation algorithms, I've been harping on, we need to think about this idea of lower bound, because we're minimizing one of the lower bound. So let's look at this problem a little bit and sort of stare at it and say, okay, we know we want to find some And a tour you think of as an abstract cycle. So let's just draw it like a cycle. It's not really a cycle of the plane. It's more windy. But it's some kind of cycle, right? And you want to find these objects. And of course, you can imagine that I've just removed one edge from the cycle. That only reduces the cost, which is good because I'm finding more nodes. So let's imagine we remove some edge from the cycle. So we go from there. Did I remove an edge? Yeah. Okay, so I removed one edge here. So I haven't done anything yet. And I make the second observation, oh wait a second, this is a path is a special kind of tree. If I have to minimize, I have to find that's always going to be worse than the best cost tree, because every path is a tree. So now I can think of going to the tree. So maybe I don't know, maybe my tree looks like this. So what I've said is now that the cost of this tour, let's call this opt, the cost of opt for a path, which is greater than or equal to opt for a tree. So far I haven't really done much. I've just made some quick observations. But if I told you the following problem, I give you a collection of points with distances between them, and I want to find the best cost tree that connects them all up. Have you heard of this problem before? It's a window spanning tree. And we know how to solve that problem, don't we? That's easy. You've seen greedy algorithms for that problem. So this we can solve. This is just the MST. So in other words, if we take our input and we compute the MST on it, we are guaranteed that the MST is a lower bound on the optimal solution. But that doesn't give us what we want. What we want at the end is a tool. So the idea is that somehow this lower bound, this MST that we compute, has to be massaged into an actual solution that we can somehow relate the cost of to the cost of the MST itself, and then the opt is kind of stuck between them and we win. We get our approximation out. So now our problem has become not solve the TSP, but find a way to convert a tree into a cycle. Because if we convert this tree into a cycle and somehow figure out what the cost of this resulting cycle is, we'll have some handle on the problem. Okay? And this kind of groping in the dark is, again, the normal way of dealing with these questions. So what might be a way to convert a tree into a cycle? What might I try to do?
Whenever there is a branch, I duplicate it and make it like in one line.
So, okay, so let me draw a simple example. Explain to me what you're trying to say. So I'm going to make a simple tree. Okay, now what do you want to do? Let me label them.
Yeah.
Okay, what do I do now?
I write A, B, C, and B and D. I'm increasing it, but then I can make it into this.
Like this?
Yes.
And then A again.
Yeah.
So you're saying go this way, go that way, come back up, go back down, come back up. I guess technically go back to B and then back to A.
Yeah.
Right?
Oh, okay. Yeah.
Is that what you're saying?
Yeah.
Okay. What is the resulting tour? Well, this tour keeps repeating things. So if you're making a tour, we'd say, okay, I visited A, I visit B, I visit C, I've already been to B, I won't visit that again, I go to D. I've already visited B again, and I go to A. Right? So I already visit, I don't have to go there again.
Go there, okay.
I mean, it's not as if I'm only sitting on a graph. The graph was what I artificially constructed. But the points are everywhere. I can go from anywhere to anywhere. Right? We'll assume in this idealized salesman person problem, you can go from anywhere to anywhere. Right? So you can do this. And here's the first observation, right? That this new one, A, B, C, D, A, is always going to be of lesser distance than the A, B, C, B, D, B, A. Because of one property. Remember the triangle equality? Remember the intuition for the triangle equality? Shortcuts are good. I'm just taking shortcuts here. In particular, if we looked at, so for example, I went from B to C to B to D. Okay? So that looks like going from B to C, then back to B, and then down to D. Right? And what I'm saying is that instead of that, I could just go B to C to D, which would be I go down this way, and then I go that way, right? And so in particular, what I'm saying is that I can replace this plus this by this. But that's a triangle inequality. That's what I just said it is. So this always reduces the cost. Is that a question? Yes?
If it follows the distance and metric.
If it, what does that mean?
Follows the distance metric.
I don't know what that means if it follows.
I mean, it can be possible like the distance between the city C and D can be moved
Much more.
in the sum of.
That's right, but then this would not be a metric.
Yeah, that will not.
That word metric is a very special word. Right. So I'm only assuming our metric. We'll talk about what happens later on. Good. So you all agree that I can make this cheaper? Okay, so this is a good idea, but is there a way to make this more systematic? I mean, I did this example, it worked fine, but what is this? Yes?
I have a question. So do we want any cycle or the cycle which joins all the nodes?
We want a cycle that visits all the nodes. That's the traveling cycle. Right? If we just wanted any cycle, we could just go somewhere and come back. So we want a cycle that visits everything. So how do we make this more systematic? Yes?
Add one edge which is like minimum of the edges which is not added in the tree.
Okay.
Select that edge and add that.
And then what will happen?
And remove some other edge so that.
But this is a minimum spanning tree. You can't do that. The fact that this is a minimum spanning tree means you've already done that already.
We are trying to form a cycle.
Yes. But you just remove something there.
Okay, so don't remove.
Don't remove. So add some edges and don't remove. Okay. Yes?
Do a breadth first search and travel in that order.
Do a breadth first search and travel that order. So, breadth first search or depth first search?
Sorry, depth first.
Yeah. So the idea is that take the tree and do a depth first search on it. Which is basically what we're going to be doing here. Right? There's going to be a depth first visiting order of the nodes. That's great. But what I want to do is not just visit them, I want to figure out the cost of what I'm doing. So let me add some extra information to this tree to capture the fact that I'm doing a DFS. So what I'm going to do is the following. I'm going to take my tree, we'll take this example here, okay? And I'm going to draw it again. I'm going to draw it here. And what I'm going to do is, I'm going to duplicate every edge. So I'm going to add a new edges to everything. Okay. Now, something very interesting has happened to this tree. The degree of every vertex is now even. Why? Because I double the edges coming out of every node. No matter what the initial degree was, the new degree will be even. A graph in which every degree is even is a very special graph. I don't know if you've heard of such a graph. Anyone?
Even graph?
No. It is not an even graph. That would be nice, but that's not true. It's a good guess. We prefer fancier names for a graph. A graph in which every degree is even is called an Eulerian graph.
I like even graph better.
I don't think Euler would be very happy with it. Euler was actually a person. Leonhard Euler, by some accounts, the father of graph theory. Yeah, you don't mess with the father of graph theory.
Different Euler's constant?
Same Euler.
Oh.
See, now you have respect for Euler.
He already has a constant. He doesn't need another graph.
He has a lot of things.
That's true. But by that logic, you remove Gauss from everything because he just took control of every single thing. So an Eulerian graph is named that way because it has a special property. that there is a way to traverse every edge in the graph without repetition. And in this example, you can kind of see how that's going to work. Because I've duplicated every edge, once I go into a node, there's always a way to come out. Because it's even, right? Every time I come in, there's a way to come out. Every time I come in, there's a way to come out. Okay? So this graph is guaranteed to be Eulerian. So I can find a way to visit every edge of the graph and get back to the beginning. And in this case, it would be basically, I visit A, and then B, and then C, and then B, and then D, and then B, and then A. Now this is an Euler tour in that it visits every edge exactly once. It visits the vertices over and over again, but it visits every edge exactly once. Okay? What is the cost of this Euler tour? How much distance am I traveling this Euler tour?
2 times the minimum standard.
Twice the MST, because I've duplicated every edge. Okay. So this Euler tour has cost which is twice the MST. Okay, so the cost of this tour. Now I'm going to do short circuits because I can do it because it's a metric. So I can actually visit every node exactly once. What will happen to the cost? Does it go up or does it come down? It comes down because I'm short circuiting. So once I short circuit, let me go back to black now. The cost of A, B, C, D, A is going to be less than equal to 2 times MST. Right? Okay. But this is a tour. We have an algorithm and a tour. The algorithm is compute the MST, double every edge, do a BFS on it, short circuit everything, and return the answer. What is the approximation ratio given by this algorithm? Well, we know that the algorithm cost, right, which is the cost of this tour here, is less than or equal to twice the MST. We also know that the minimum spanning tree is less than the optimal cost by the argument we made earlier. So we have a two approximation. Because we've just proven that the algorithm is less than or equal to twice the optimal solution. Obviously, it's more than the optimal solution because it's minimization. So you see what just happened here? We took our problem, which was find this cycle, and we converted it to a problem that we do not solve, completely MST. And then we said, okay, we know that this MST is a lower bound, and we can massage it to get an algorithm whose cost can be expressed in terms of the MST. That gives us the answer. Any questions so far? Yes?
So you shorted C and D edge as well as D and A edge?
Well, there was, so in the blue tour, I'm going A, B, C, and then I'm saying, oh, go back up to B and down to D. And I'm saying, well, I've already been to B, I'll just go straight across to D. So it becomes A, B, C, D. And then from B, and then from D, I was going back to B to A, like I've already been to B, so I'll just go straight from D to A. So A, B, C, D. That make sense?
Yeah.
Excuse me, this blue one is not Euler path.
That's the Euler path. That's the Euler tour. The blue one is the Euler tour.
So the
Euler tour visits every edge exactly once. It can visit vertices multiple times.
we don't need to have nodes with even.
If your graph consists of all nodes, if all nodes in your graph have even degree, there always exists an Euler tour. And the proof is, if your graph consists of all nodes of even degree, start at any node, okay? Take any edge going out. Every time you enter a vertex, there is always a way to exit, because every node is even degree. Eventually you'll get back to the starting point. That's the only one left. It's not that simple, because you could create a collection of cycles, you don't need them together, but that's basically the idea. Yes?
So in our short circuit, we went A, B, C, D, then we just jumped there, is that?
Right, so what I'm saying is the following. So let me just, so here in my Euler tour, I went A, B, C, I visited B already,
Okay.
so I'm going to jump across to D.
Ah.
And then I visited B already again, so I'm going to jump across back to D.
Got it.
And that gives me.
And then on our inequality also, what is this I mean, we know that we're less than 2 times the optimal solution, but
2 times MSE, yeah.
yeah, right. So, but do we know that we're even above the optimal solution?
Yes, because if you're minimizing, you can't be better than opt. Opt is the best possible. Opt is by definition the best possible.
Sure.
Anything you do is by definition only at least as much as the optimal.
Oh, right.
Because if you're better than that, you're optimal.
It's not actually.
Yeah.
Okay.
So in minimization, you're always above opt. You can never by just by definition, you can't be below the rest. The best is the best. The rest is the best. Yes.
How do you do this short circuiting, like randomly or?
No, you just do it exactly as I said. I mark off every vertex that I visited in my Euler tour. So I marked off A because I visited it. B marked, C marked. Now my Euler tour says go back to B. I said, oh wait, B is already marked. Go to the next one. That happens to be D. D is not marked. Okay, so continue. And so on. So it's just a build day structure. You just build a little bitmap saying have I visited this or not.
But it's like why do we start with A and then say if A was connected to 2 vertex, then what would we choose?
Doesn't matter. It's an Euler tour. It's a cycle. This is a cycle. It doesn't matter what you do. You can start anywhere. You can start at C and do the same thing all over again. The reasoning will still remain the same. Like I could go C, B, D, A, C. That would still be fine.
And if a vertex is connected to 2 other vertex, we choose.
It doesn't matter because in the Euler, remember I'm only looking at the Euler tour. The Euler tour is a cycle, is kind of it's a walk, right? So I just look at that. That's a sequence. I don't care what else is happening. I'm only looking at the edge going from A to B. I'm only looking at the edge going from B to C. If there are multiple edges, I'll visit them later because it's an Euler tour. I'll worry about that edge when I get to it. Yeah? Okay. Can we do better? Where is this factor 2 coming from? I doubled every edge. Why did I double every edge?
So we wanted the even.
Why do I want even?
We wanted to make an Euler,
Why do I want to make an Euler?
so we could make it faster walk
Okay.
to guarantee that.
Can we do something else to make that happen? We double the edges to make an Euler to make a tour. Can we do something else to make an Euler?
About making a clique.
Making a clique. Keep going.
Because clique will have less, I mean it may have less number of edges than.
But a clique does not. A clique could have all vertices of degree odd. If you have a clique of size 4, every vertex has degree 3. So let's look at our tree again very carefully. Okay? Let's look at our tree. Let's look at the degrees of all the vertices. I mean, this was not Eulerian, so we had to write down the degrees. So the degree of this is 1. The degree of this is 3. The degree of this is
1.
So there are 4 odd degree vertices. Right? Well, then somebody in a different tree. So this is degree 2, 3, 3, 1, 1, 1, 1. 6 odd degree vertices. Based on 2 examples, I will now propose a claim. Every graph has an even number of odd degree vertices. You may have heard this before. This is called the handshake lemma. It's called various things. Every graph has an even number of odd degree vertices. Do you know why?
Each vertex.
The sum of the degrees has to be even.
Why does sum of degrees have to be even?
Because of vertex.
Why? What is the sum of the degrees in a graph?
Oh, yes, and it's equal to.
Sorry, go ahead.
It's the 2 endpoints. You got an endpoint going one way and an endpoint going another way.
You're just double counting, right? It has to be even. The total sum of all degrees in a graph is twice the number of edges. Twice. Even. So if the sum of all the degrees is even, and obviously the sum of the even degrees is even, what's left? The sum of all the odd degrees, which also has to be even. So So the sum of all the odd degrees is even. I think you were just about to say, now you can connect them up somehow. How would you connect them up? So I have a bunch of odd degree vertices, like in this case I have 4 of them. What's the minimal amount of work I need to do to make them all even? 3 edges? Even less than that. 2. How would I do 2?
The ones the child has.
Sorry?
Are you talking about the left graph?
The left graph.
Oh, never mind.
Add a self loop.
No self loops. We don't like self loops. That's just too nibble-geared.
You can do 1, right?
2.
No, 2. You have to do 2.
Yes.
Connect the 2 bottom ones, and then connect the 3 and the top one.
Am I now Eulerian? Have I added fewer edges? Okay, good. What about the next one?
You just take pairs of odd vertices.
Take pairs of odd vertices and connect them up. What does that sound like to you?
A greedy algorithm.
A bipartite matching. It might sound like a greedy algorithm. I can't presume to speculate what you hear when I say it, but it's also a bipartite matching. So you have, okay, good. So here's the new idea. We have all these odd degree vertices, and there are an even number of them. So we can match them up. And if we have to take matchings, why not just take, since we want to add edges that have as little weight as possible, let's take a min-cost matching. Right? So maybe this is the min-cost matching here, here, and here. And now we know the graph is Eulerian. We may not know quite what it looks like, but we know it's Eulerian. So the same trick as before works. How many edges have I added in terms of the optimal TSP tour? That's the problem, right? I mean, I add all these edges, but I need to somehow relate this to the optimal tour. With the MST, I could do that. But with this, what do I do? To answer that, let's go back and look at the optimal TSP tour again. Okay? So this is the optimal TSP tour. Let's just make it 6 for now. You'll see why. Do you see a matching in here? Do you see a matching anywhere in this cycle? Watch. Is that a matching? It is? Yes? It's a matching. It's a matching in a graph. It's a set of edges that are all disjoint from each other that connect up the vertices. In fact, it's a perfect matching.
But it's already connected there.
Sure, but it's also matching. I can also overlay this matching on top if I want to. Wait, you'll see them. I'm going to pull a little rabbit out of my hat now. Hold on. Let me also draw the other one. That's also matching. Let's say it's even for now. Right? Okay. So now we can say, look at the cost of the blue matching and look at the cost of the red matching. So we can say in this graph that the blue matching plus the red matching is equal to opt. Right? What can we say about the cost of these matchings? Think pigeonhole principle. Here's what we can say. Right? If two things add up to a number, at least one of them must be as most half. Right? Okay, but remember what we were computing in that graph? We were computing a min-cost matching, weren't we? The min-cost matching is the best matching possible. It has to be less than one of these two. So the min-cost matching is less than equal to the min of b comma r, which is less than or equal to opt over 2. Okay? All right. So where are we going with this? Let's summarize our new algorithm. This is not very confused right now. So the algorithm says this. Number 1, compute MST. Number 2, find all odd degree nodes. Number 3, compute matching on odd degree nodes and add to MST. Compute Euler-Tor and short circuit. So this is the same as before, and this is the same as before. This part has changed. Instead of just doubling the graph to get the Euler-Tor, we're doing this extra 2 steps to get the Euler-Tor. But otherwise, the basic analysis is the same. And what does that mean? That means that the cost of the algorithm, right? So the cost of the short-circuited Tor is less than or equal to the cost of the Euler-Tor, right? But the Euler-Tor consists of all edges in this graph, which is equal to the MST cost plus the matching cost, right? Which is less than or equal to opt plus opt divided by 2. We have a better approximation. We have a 1.5 approximation instead of 2. This algorithm is so famous, it was developed in 1975. I think I got the spelling right, by Christofilis. And this is called the Christofilis heuristic. It's a very, very effective method, even in practice, for computing a reasonably good traveling salesman tool. Because it's so fast, you just compute it. MST to a matching. Yes?
So, does that mean after you do a mismatch matching, the solution we got from not doing the matching is different? Because in that case, you did depth first search, right?
You still, well, the depth first is just the Euler-Tor.
Yeah,
either way, you still do the Euler-Tor the same way. But the graph you do the Euler-Tor on is different. In the first case, the graph you do the Euler-Tor on was this double graph.
Yes.
Here, the graph you do the Euler-Tor on is this MST plus matching graph.
And this guarantees that there's a path like this.
But it's an Euler graph. It's an Eulerian graph.
Oh, it's not.
It has to have one.
It has to have it. Oh, okay.
That's why the Eulerian property was the key property. We just found a different way to get there.
Okay.
Okay.
So we reduced both the minimum of the bounds and we're saying the cost also reduced.
Well, we're saying the cost reduced. That's all we're saying. The cost of the algorithm, because you get a better guarantee.
It's bounded by a better guarantee, but sometimes that could give you a better solution.
Sure. Worst case.
Yeah.
This algorithm stood as the best known algorithm for TSPs from 1975 till last year. Yeah. This simple algorithm. And last year, someone got it down to 1.5 minus epsilon for some really tiny epsilon. And then in a flurry of activity there, I think it went down to 1.461. And I think it's now at 1.4. But for a long time, people thought this was no way this could happen. So there's room for improvement. One of the good job security features in approximation algorithms is that if you make any improvement, even the third decimal place, you get a new paper out of it. You can produce many papers that way. I just realized that all this stuff is being recorded, so everything I say like this is it's going to get me into trouble. Oops. Huh? Yeah, that takes even more work. So.
I don't think Euler is going to get upset about anything you say, so it's probably fine.
Euler might not, but the entire community of people who work in approximations are probably going to come and scream at me. Sorry.
Weiler's on your side.
Okay. I'm happy now. I have an approximation on the TSP, and I feel the power flowing through me now. So like, what's with this nonsense metric constraint? Let me just move forward and beyond all the way and throw out this metric constraint. I don't need it. Who needs metrics anyway? We can do it whatever. So let me define the generalized TSP problem. So in the general TSP problem, I have some matrix. I have some distance function, again as before. X cross X going to R. But it's not necessarily a metric. It may not satisfy triangle equality. It may be the case where going directly is way worse than going through this thing. For example, if you fly by plane, sometimes it's a lot cheaper to go here instead of just going straight. Right? So if you're thinking of doing a traveling salesman tour by plane and you want to minimize the amount of dollars you spend, then this is an example of where you would not be getting a metric problem. What can I do now? Can I get an approximation? And here's where things start getting interesting. I'm going to show you now that forget 1.5, forget 2, forget log n. I cannot give you any approximation guarantee for solving this problem. Even if it's 1 billion. Even if you want a solution that's 1 billion times the optimal solution, I cannot give it to you. And I'm going to show you that the problem of getting an approximation algorithm for this TSP is NP-hard. Yes, that's what I said. I have an NP-hard problem and I want to get an approximation for it, and that's also going to be NP-hard. Okay. And the way we're going to do it is by solving a problem called Hamiltonian cycle. So the Hamiltonian cycle problem is the following problem. I give you a graph, and I want to find a tour visiting each vertex exactly once. So, for example, this graph has a Hamiltonian cycle. This graph does not. Can I tell them apart? Given a graph, can I tell you if it has a Hamiltonian cycle or not? So it's not so much find a tour or say no. So find a tour would be the yes instance, and otherwise say no. You can't do it. Okay, so this is called Ham cycle, Hamiltonian cycle. Notice that the Hamiltonian cycle problem is very similar to the Eulerian cycle problem. Instead of saying I want to visit every edge exactly once, I want to visit every vertex exactly once. But the Eulerian cycle problem is easy to solve. Check if all the vertices of degree are equal degree in a time. This problem is NP-complete. Much harder. Okay. And you'll have to take my word for it because I've not proved that. But again, I'm going to show you that if I could solve the TSP with any approximation guarantee, I will be able to solve the Hamiltonian cycle. I will be able to decide yes or no. And here's the proof. So I'm going to take my graph G. Okay. So let's say I want to get. So let's say I want to get a C approximation. Okay. I might have to fiddle with these numbers a bit. So I'm going to take my graph G, which I'm going to reduce to the TSP problem, and I'm going to say for if U comma V belongs to the edges of G, then distance from U to V is equal to 1. And if UV is not in the set, then distance from U to V is going to be C times N. Okay. I can do this because I'm allowed to arbitrarily decide distances for every pair of vertices. I don't have to worry about if they satisfy triangle equality or not. In particular, in this case, this will not satisfy triangle equality. Because if I have two edges in my graph that look like this, then in the distance problem, it would look like this, right? I would have 1, 1, and I would have C times N. This obviously does not satisfy triangle equality. Right? Because it's much cheaper to go roundabout than to go straight. So this is my reduction. I take a graph, I construct a distance function, and I compute this. Okay. suppose I get, and now I say the following. Let me see. So let me say what's going to happen now. If my optimal tour has cost less than equal to n, then there's a Hamiltonian cycle. Right? If the cost is more than or equal to Cn, then there is no Hamiltonian cycle. Can you see why? Because if the solution to my tour uses only edges from the graph, then my cost will be n. Because I visit every vertex exactly once. It's a cycle of length n. The cost is n. If I use even one traversal that was not in the original graph, I'm going to pay Cn. And I may have got off by 1 here, but I'll pay Cn plus n minus 1. So that's C plus 1 times n. So even more. So you agree with these two statements? Okay. Suppose I had a C approximation. So let me actually make this. This is going to be really. This is going to be C plus 1 times n minus 1. Because it's Cn plus n minus 1.
In the first case, it will be exactly n, right? How could opt be less than n?
Yeah, I'm being lazy. You're right.
Okay.
Suppose I had a C approximation for the TSP tour cost. What's going to happen? Think of it this way. This is the line for there is a Hamiltonian cycle. That's an n. This is the line up here for there is no Hamiltonian cycle, which is C plus 1 times n minus 1. Suppose I got a C approximation and my number was less than C plus 1 times n minus 1. Suppose my number was somewhere down here. Then what can I say? Yes?
I have a doubt.
Yes.
So you said that the opt is equal to n, and like 1 is the cost associated with one edge.
Yes.
So we are covering all the edges.
No, because if you take a cycle that visits every vertex, how many edges will it have? It'll have n edges, right? One for each vertex. The number of edges could be whatever. N is the number of vertices. If I get a C approximation intuitively, then if there actually was an optimal solution of size n, my approximation algorithm, even if it's bad, is never going to get any worse than C times n. Because it's a C approximation algorithm. By definition, if there's a good answer of cost n, I will get an answer of cost at most C times n. If there is no Hamiltonian cycle, then the best my algorithm can do is get C plus 1 times n minus 1. What does that mean? That means if I have a C approximation algorithm, I can tell the difference between the no and the yes instances. Right? So I run my algorithm, I look at the cost. If the cost is C times n or less, I say yes, there's a Hamiltonian cycle. If the cost is more than C plus 1, I say no, it's not a Hamiltonian cycle. And my algorithm will be correct, because it's guaranteed to be a C approximation. So coming up with a C approximation for TSP must be NP hard, because I could use it to solve the Hamiltonian cycle, which isn't. But I didn't tell you what C was. C could be anything I want. I can make C a billion. So what I'm saying here is that I can give you an example of a problem where getting any approximation guarantee for the problem is NP. And this kind of setting here, where you have this gap between the no instances and the yes instances, is called the gap problem. So this problem is technically called gap TSP. So what we've shown is that gap TSP is NPR. And the gap directly relates to the approximation guarantee we want. If we want to show that you can't get a certain approximation guarantee, you need to show that the corresponding gap instance is NP1. Yes?
So in this case, since it's a TSP, I could have gone, my solution is always bounded by 2 MST, right?
No, it's not a metric. That only works for a metric space. This is a non-metric TSP.
Yeah, but if I'm going to this, I get once I have a minimum spanning tree.
There's no minimum spanning tree. There's no metric. I can't make that guarantee anymore. Once I take my MST and I try to short circuit it, my cost will blow up like crazy because I don't have a metric structure.
I won't short circuit it, then I have.
How are you going to do it?
I have 2 MST, right?
But how are you going to? No, how are you going to do 2 MST? You got the 2 MST because you took the MST, you doubled every edge, and you traversed it and short circuited things. If you don't short circuit, you don't have a tour. You have to short circuit to make a tour because otherwise you're visiting vertices multiple times.
And this I should not visit.
You're not, a tour does not allow you to visit vertices multiple times.
But if I visit them, then I have a better approach. Then I won't end up with it.
Yeah, but it's not a tour. It doesn't mean you can produce a tour. Yes?
Well, you are changing the specification of the non-metric space by whenever you want. You say yes.
Yeah.
So, I mean, that seems a little strange. I mean,
why?
When you have a non-metric space,
it's not a metric.
They're somehow fixed. I mean,
it's not a metric. All I'm saying is that imagine this. Suppose I had an algorithm for TSP that worked regardless of the distance structure. Then I would solve the algorithm. That's what I'm saying. Maybe there are other spaces with other metric structure like things that I can work with. And there are. But in general, I can't do this. In general, it's problem solving.
Yeah, solving is thinking in a very, very general form like the.
But I've proven now. You might say might be, but I have a proof. But I have a proof. That's the point. I can prove it. And not just that it's hard. It's not that it's NP hard. It's NP hard to get even an approximation to it, to get even close, to get within sniffing distance of the answers that we are.
So what does that mean? That means that there is no way at all to find the answer for this.
Kind of depressing, isn't it? Yes, that's what it means. There is no way at all. In general. Maybe there are specific instances where you use it, but in general there is no algorithm.
So is the proof of being impossible to find the answer?
Sorry?
So is the proof of being impossible to find the answer for such a problem?
That's what it is. In fact, there is a, okay, so
what's
jumping
the
in.
corresponding decision problem, like for the approximation side, is the question, is there...
It's the gap problem.
But is there a 2 approximation?
Okay, so if you want to say, is there a 2 approximation for vertex cover or not, then the question you're asking is the gap problem for vertex cover, where my graphs all either have a vertex cover of size k or of size 2k, is that problem NP hard? If deciding between k and 2k is NP hard, they're getting a 2 approximation of NP hard by design. That's why we think of these gap problems. The decision version of an approximation is a gap problem. Okay? So the picture, if you know, we're getting somewhat towards the end of the course, right? So it's always important to plot this graph, right? So this graph is time, x-axis, and the y-axis we're going to plot happiness. Okay. So we start off with the class after the initial shock of realizing, oh my God, there's actual math in this class, which means there's a little bit of unhappiness. Then we said, okay, we're learning some algorithms. We're all happy. We're dividing conquer, dynamic programming, flows, greedy, randomization. We're all happy. And suddenly you're like, oh my God, NP hardness. And then I said, oh, but wait, we can do approximations. We're all happy about that too. And of course, since everything that goes up must come down, this is what is called hardness or approximation. That's what we're talking about today. The fact that you can't solve it, you can prove it's NP hard, you might have an approximation, but you can't even do that. That's where we are today. And one of the most sort of beautiful set of results in the last 25 years in this area has been, in fact, to show that you can actually say things like this. That you can actually say that there are problems that you cannot approximate. And in a very systematic, very elaborate way, and very precise problems. And to show you a flavor of that, I want to introduce yet another problem, which will be the example of SAT for this regime. So SAT was the canonical NP hard problem. I want to introduce the canonical problem that's hard to approximate, which is also a SAT-like problem. So you all remember SAT. Hopefully you all remember 3SAT, right? You have clauses C1 and C2 up to Cm. Each clause consists of 3 literals, x1 or x2 or x3 bar and so on and so forth. And you want to satisfy a set of clauses. Let me define the problem max 3 sat as follows. Max 3 sat says find an assignment to satisfy as many clauses as possible. So, in other words, in SAT, the question was satisfy everything or less than everything. It was a binary thing. Here I'm saying, okay, look, I know I may not be able to satisfy everything, but just do as much as you can. Get up to about 70% of the satisfying assignments, I'll give you the whole thing. Well, maybe I won't. So you answer the question. You want to find an assignment to satisfy. Of course, if it was actually satisfiable, you could satisfy all of them. But maybe you can't satisfy it. There's a really simple algorithm for this problem to get a good approximation there. And the solution is in one line. Done. They do the dumbest thing possible. Assign them randomly to be true or false. What is the probability that any particular clause is satisfied? Sorry?
Wouldn't it be somewhere like 50%?
Some of the products go, right?
Each clause has 3 variables in it. Exactly 3. What is the probability that a clause is satisfied? 1/8 is one answer.
Probably 7/8.
7/8 is the other answer. I can safely say that only one of these 2 answers is correct. I only give you information. I'm implying that 4/8 is not correct. Yes?
Well, you basically, any clause will be correct as long as at least one of the variables is true.
Okay.
And so you have 3 variables and each has a 50% chance of being true.
So the only way you mess up is if they're all false, which happens with probably 1/8. Therefore, the probability of success is 7/8. What is the number of clauses you will satisfy with this algorithm in expectation? Each clause is satisfied with the probability 7/8. What is the probability? What is the expected number of clauses satisfied?
7/8
times n. Linearity of expectation, right? So the expected number of clauses satisfied. Okay. Can we get an upper bound and opt? There's a maximization, so we need upper bound and opt. What's upper bound and opt? How good can opt be in terms of number of clauses satisfied? Huh? Could do all of them, right? And so they're n. So opt is less than or equal to n. The algorithm is in expectation is greater than or equal to 7n over 8. What's my approximation guarantee? 7/8. It's a maximization, so the approximation guarantees are less than 1. 7/8. Here's the thing. To do any better than this is n. This is trivial. This was a result that was shown essentially through a series of papers in the early 90s. That for this problem, you cannot, first of all, you cannot get an arbitrarily good approximation. And later on, it was shown that in fact, this is the best you can get. This is dumb algorithm. If you did anything better, you could solve it. So just like SAT was the canonical NP-hard problem that we use as the source of all evil to make other problems NP-hard, this is the source of all evil for approximation hardness. Why? Because what is it saying? It's saying that, essentially what it's saying is that to distinguish between
Great.
That's what it is. It's a gap space.
But at the same time, it's also giving a boundary dependency, right? If I'm using this as a SAT problem, does that mean all the gap problems also have like some kind of...
No, they blow up.
They blow up.
So here's the thing. What we'd like to do is build a theory of reductions for approximations the way we did for NP hardness. Okay, so for NP hardness, we had this set of reductions. So, okay, I have a hard problem. You know, I have another problem. I reduce the hard problem to my other problem. Must be hard because this was hard. But hardness, in the NP hardness sense, is a binary thing. It either is or isn't. In an approximation sense, you have actual numbers involved. And you want to transfer these numbers correctly. So you actually need the notion of a reduction that preserves the approximation guarantee in some way. Maybe it blows up by a fixed amount or reduces by a fixed amount. You can't just use a regular NP reduction. Because the NP reduction could change things just by one. There could be a difference between having everything satisfied or everything minus one satisfied. And everything minus one will not give you an approximation gap. You need a large gap. So it was not trivial to come up with problems that had large gaps. It was a big breakthrough when this came along. And the story of this is a very interesting story that will have to remain secret for some other time. But the result that proves this is actually a much deeper result about how to prove things. It has nothing to do with approximations. But it basically says that if you have a theorem and you want to prove it to me, you can write out a proof in binary. I will look at 3 bits of your proof, and I will know if it's true or not. It's called the PCB theorem. So you take your proof, you write it in a special format, and I look at it in 3 bits. I look at 1 bit there, 1 bit there, 1 bit there, chosen at random. And I will do something with those 3 bits, and I will decide whether your proof is correct or not. And I can do this with high probability. It's called the PCB theorem, not after the drop. Probabilistically checkable proofs. And that's what it's saying. And that allows you to show things like this. And again, how that works is a bit complicated. But that's the main result, that you can check proofs very quickly, and that allows you to show that there are problems that are intrinsically hard to approximate. And I want to give you one example of how you can do this. I want to show you that using this problem, I can show that the clique problem, finding the largest clique in a graph, is hard to approximate. Okay? So before I go on, any questions? About what I'm trying to say? Yes?
Well, it seems so natural to have this problem, for these problems to be very hard, because, for example, we cannot solve them in polynomial time. You are saying that what is the largest possible, the way that we say the problem is kind of very hard to say that. What is the largest? We can have some kind of, okay, this is the largest in that item, but what is the real largest?
Okay, so it's very natural this could happen.
Yeah.
Have you heard of bin packing? Bin packing. Bin packing, not balls and bins, but good, I'm glad you remember that. Bin packing is the following problem. I have a bunch of objects, each of size less than equal to 1. And I have lots of bins. Each bin is a size exactly equal to 1. What is the fewest number of bins I need to put all my items into store? Right? Because they may not always quite fit, and there'll be some overlap. I can't go over the limit. Each bin only carries up to 1 unit of items. So this is again an NP-hard problem. Your reasoning exactly applies. It's going to be hard to find the smallest number of bins. But I can get to within opt plus 1. Whatever the optimal solution is, I can get to within 1 of that. Maybe for all problems I can do that. Maybe for all problems I can get within 1 of the correct answer. Maybe for this I may not be able to satisfy all of them, but I can get all but 1. It's possible. What this result is saying is that no, it's not.
It seems to be a bit different because, for example, you have some sort of constraints over the kind of, for example, the bin packing. You know that what is the size of the objects.
It's NP-hard. From an NP-hardness point of view, it is exactly the same as SAT. They are equivalent problems. But when you look at things through the lens of approximation, all these problems that look the same, they suddenly start changing in complexity rapidly. You have your PTASs, you have your well-behaved dynamic programming approximations here, your bin packing, your knapsack, you have your vertex covers and your TSP metric spaces here, you have your set covers up there, and then you have your label covers up here, and then right at the top you have TSP with no metric and you have clique. And you have independent set. You have things that just make life very sad. There's a whole spectrum of things in the middle. There's things which have approximations that are log star n. Have you ever heard of log star n? If you take a number and take log repeatedly till you get down to 2, the number of times it takes you to get there is log star n. There are problems which have a log star n approximation, and that's tight. Getting better than that is NP-hard. There are very weird beasts in this space. So it's like we had this flat space of NP-hard problems, and they all separate out based on the approximation problems. So that intuition is okay, but it doesn't really, I think there's a bit of hindsight there. We didn't know that these problems existed this way. And this fact said, oh look, there's this huge hierarchy inside what is a flat landscape that's telling us of the relative hardness of certain problems. And that's very important from a modeling point of view, right? When we have choices about modeling a problem, we could choose to model a problem so it becomes NP-hard, or we could choose to model it so it's Polynomial time. And that's one lens. But let's say every way we try to model it is NP-hard, you could again choose to model it so it has a reasonable approximation, or you could choose to model it so it doesn't. And again, so that knowing that lens, and knowing that it exists is very important. That there is a hierarchy even among problems that are NP-hard. That there are good NP-hard problems and bad NP-hard problems. Okay. So we want to show that the clique problem is hard to approximate to within any constant factor. And if I've never mentioned clique before, again I have a graph, and I want to find the largest clique. A clique, of course, is a subset of vertices that are all connected to each other, right? So this is a clique of size 3. This is a clique of size 4, and so on. I want to find the largest possible clique in the graph. And you can see why this might be hard. I may have to enumerate everything. It seems like it's a difficult problem. The clique is NP-hard. But I want to show you how to show that clique is hard to approximate by using this 3-sat sum. Okay? And so what I'm going to do is, since I know that 3-sat is hard to approximate to within some error, I'm going to use this instance. So I'm going to say, okay, I'm going to construct a graph from my 3-sat instance, and I'm going to do the following. So take my clause. So I have a single clause. Let's say it's x1 or x2 or x3. Right? And what I'm going to do is I'm going to create 7 vertices. 2, 3, 4, 5, 6, 7 for this clause. With the property that each vertex corresponds to some assignment of values that would satisfy that. So in this case, x1, x2, x3, it would be, let's see, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Any of these assignments to x1, x2, x3 would satisfy this clause. Okay, so I can write the next one. Maybe this is not x1 or x2 or x4. And I do the same thing there. And again, there's 7 more there. Okay? And now I connect up 2 vertices if their assignments were compatible. That means if the assignments for x1, x2, x3 here were the same as assignments for x1, x2, x4 here. Of course, x1, x2 will get back. So I have this graph. Okay? And I now say, what is the size of a clique in this graph? So notice that, you can only pick one vertex from every row because they're not connected to each other. They're an independent set. So you can't have a clique of size more than m, the number of clauses. So if there are m clauses, you can have at most one vertex from every row in the clique. So it could be at most m. And in fact, if this instance is satisfiable, there is a clique of size n. Because if this instance is satisfiable, then there's a way to set these variables consistently, one for each clause. And since they're consistent, we'll put edges between them. So we'll have a clique. So if the instance is satisfiable, the clique of size n. Suppose there's a clique of size k, right? And again, you're only picking one vertex from every row. That means you're only satisfying k of those clauses, right? So a clique of size k implies satisfying k clauses. This is an approximation preserving reduction. that the same number that you get here, get you there, n, m, k, k. What does this mean? We know that approximating SAT to within better than 7/8 is going to be NP hard. This automatically means approximating clique to within 7/8 is going to be. Because if you could do clique better than 7/8, you could do SAT better than 7/8. So not only can we reduce NP hard problems to unknown problems to show them NP hard, not only can we reduce NP hard problems to other problems to show them approximation hardness, you can take a problem that's hard to approximate and reduce to another problem that's hard to approximate to show this one is hard to. So you get a whole sequence of reduction, and these reduction things are incredibly complicated. Clique, in fact, is, so just to tell you how bad clique is, this shows you can't get a constant. Here's what you can say for clique. That it is hard to approximate to within n to the 1 minus epsilon for all epsilon greater than 0. And if you have a hard time parsing that, what that means is that if a graph is a clique, it's of size n, your best algorithm will give you something like log n, which is terrible compared to n. So clique is one of the worst of the worst. If you try to model a problem and it looks like a clique, you don't want to model it because you can't even get close to that. Yes?
Would it be reasonable to consider approximation algorithms that maybe aren't, like we're talking about maximums, maybe it's not, let's see, minimums, maybe it's not bounded above by some constant times optimal, but it's bounded above by like optimal squared or
yes?
some function?
Well, we've seen, for example, set cover is bounded above by log n times optimal. So it's a guarantee that gets worse as n increases.
Right.
But it's still, and in fact, you can show that's also tight. That you can't do better than log n.
But could you have an approximation algorithm that's maybe not some factor times optimal, but like some other kind of
op squared. So
yeah.
I've seen papers where people show the approximation that the algorithm solution is something like opt times opt. Yeah, that definitely happens. Sometimes that's all you can show. It's not as satisfying. Because you can't give it a nice clean bounded, it depends on off, which is annoying. But yeah, if there's nothing else you can do, then that happens too. The idea of an approximation, there's nothing special about saying it's a constant or not. So you're absolutely right that you could try to relate this in this manner. And it depends on the problem. Like I said, the problem.
For TSP, the general TSP, is there maybe an approximation algorithm who's not bounded above by some constant times off, but maybe it's bounded above by like op squared or
I don't think we can do that because the Ham cycle reduction, the opt value is n. I know what the opt value is. So I set up my C as n, and you'll get n approximation. I can set up my C as n squared, I get n squared approximation. Since opt is at most n, I can make this arbitrarily bad in terms of opt. It could be opt to the 100.
Yeah.
So yeah, so it's horrible. Yeah. So that doesn't work there. Yes.
Can you back to this? Okay, here, how to connect two vertices here?
You connect two vertices if they represent assignments to variables that are consistent. In other words, in both of the, so in this case, in the second case there, I have x1 bar, right? So, but maybe this assignment does set x1 bar to be 0, so x1 is actually, sorry, x1 bar to be 1, so x1 is 0. And x2 is in fact 0 as well. And x4 is 1. Now this 0 here is for x1. This 0 here is for x1. So they're compatible. This x2 and x2 are compatible. So the whole assignment is compatible. We'll put an edge. Right? There's no conflict. That's why a clique corresponds to satisfying assignments, because in a clique everything is compatible. So I have found that, just talking to students and even talking to my colleagues, right, that when you take an algorithms class, even in grad school, you tend, at least people tend not to talk about this at all. And I don't know how many of you have ever heard of hardness or approximation. Or heard of, how many of you heard of approximation algorithm before this class? Just curious. Some small number. How many of you heard of hardness or approximation before this class? Okay, so I feel like hopefully it's something that you've not seen before that you're seeing now. This is, like I said, from an, yes.
I have a question for
Yes, please.
So we're moving the tree. So in that degree for each vertex, if it's then it should be n-1.
If you have a clique of size k, then every vertex in that clique will have size degree k minus 1. Yes.
Yeah. So how would we do that in that? That means that all the answer matches for one.
Because if they're compatible, then they're all compatible, right? I think I just bring all possible compatible assignments.
Yeah.
So if I have two, so think of it this way: if I have a vertex here and here, right, in the clique, right? They're in the clique because they have a compatible assignment. So now look at, suppose I have a satisfying assignment. That means there's a way to satisfy each of these clauses by a single assignment of values.
Yeah.
So I look at those vertices corresponding to that single assignment. By definition, they're all compatible. It's the same assignment. So all of them will be connected to each other. Because that's how I constructed the graph in the first place. So you will in fact have that. You'll have a clique, you'll have every vertex will have degree of minus 1. You'll have an edge from that vertex to every other thing.
And why we didn't put 0, 0, 0 in that?
Because I only want to look at the satisfying assignments. 0, 0, 0 would not satisfy that. So you write up only the assignments, the 7 of them, that actually satisfy that clause.
So what does that clause mean? That means suppose it's a quotient and it's all or false?
Well, the clause is basically saying that clause is satisfied if any one of x1, x2, x3 is set to true. Right? That clause is satisfied if any one of x1 bar, x2, and x4 is set to true. It's just like SAT. In SAT, the same thing. Right? I have a clause. I want to make sure each clause is satisfied, so I want to make sure that one of the literals in that clause is set to true. So in the OR, I get a true. So it's the same meaning as before. Yes?
So in this problem, the graph actually that you are trying to find a clique on that is kind of knows that you.
Yes, so specially constructed from the instance of satisfied. Yes.
So it's, for example, here is 7 times n the size of the actual number of vertices of the actual.
Correct. Which is polynomial. So the reduction is polynomial, which is again important. Yes.
Don't be upset about this, but okay, so if you're setting x1 to 0 to false and then x1 bar to false, to me that's saying incompatible.
They are incompatible. Correct. But I didn't write, when I wrote the assignments, these are always the assignments to the variables, not the literals.
Say that again?
This is the assignment to the variable, not the literal. The literal is x1 bar, the variable is x1.
Okay.
So I deliberately said, assume x1 bar is 1. So x1 is 0, and that's why I get an. Those notations for the variables, not for the literals. So you're correct. It has to be compatible with variables.
Okay.
Yeah. So I should hope I don't get mad at people. Do I get mad?
No, I'm sure we asked.
Not for that.
Yeah.
Wait. Any other questions? Okay, so this, in some sense, today is the last lecture of sort of mandatory content for this semester. There's one more lecture next week on how to do binary search in a zombie apocalypse. No, I'm not joking. This is a very serious, it's a very cool algorithm, and you will all love it. Because who doesn't like zombies? Zombie apocalypse.
It involves a shotgun.
Sorry?
It involves a shotgun.
In fact, it does. I wasn't going to bring mine. So that's one more. It's another algorithmic technique that is often never taught in algorithms class because who wants to teach about zombies anyway? But it's very important, and especially in a lot of data analysis problems, it comes up a lot. And so I'll teach that next week, and then of course we have a Thanksgiving break. And after that is kind of miscellaneous stuff. So what I usually do is ask people if they want to just what they would like to hear about, and I'll just do lectures on demand, as long as it's algorithms. You don't want to hear me talk about anything else. So if you have any thoughts on that, post something in the discussion forum, email me, email the TAs, whatever, and I'm happy to oblige if I can. I have a whole collection of stand-up improv algorithm lectures I give you. So they're not funny. So I will see you all next week for zombies, and then we'll have time.
Thank you.
Because the idea is that when I wrote that, I was like, that's like guessing when the guests are very far value. So if I can get an approximation, that's close, I can spend. So if I can show because I feel love that's why I